start hit record so that we don't lose even a minute. So welcome back, folks. Happy Tuesday. Happy Garbage Day. The snow day yesterday, I will admit, was single-handedly my fault. I tempted the universe by washing my son's snow pants and putting them away in his closet because I thought snow pants would not be needed anymore, and I was mistaken. So 5 inches of snow. Put the snow pants back in the bag. Snow pants are not a thing once you get past about age 5, though, I've discovered. It's very hard to find snow pants. Mm-hmm. Unless they're for skiing, maybe. But then they're not like the cute little overall snow pants that the little kids have to wear to play in the snow. So next year, he's outgrown this year's snow pants, so it's time to say goodbye to them for many reasons. Anywho, I have open here your formative assessment number 3, which I had a chance to read and comment on this morning and update grades accordingly. So I thought we could go over these. There's still some misconceptions I want to try to clear up with respect to distributions versus link functions, because they're related, but they're not the same thing. So first up, number 1 here, how do you know what kind of conditional distribution is most appropriate for each type of categorical outcome, binary, ordinal, or nominal? So the words logit, probit, or any of those do not go into this answer. That is not the question. The question is, what type of probability distribution characterizes these types of responses? So for binary, what's the answer?
Binomial.
Binomial, or a special
Bernoulli.
Case of binomial, Bernoulli.
Bernoulli,
Yeah.
yeah.
So I would take binomial because that is for more than one binary trial. Like number correct follows a binomial distribution, but in binary it's a special case where you have one trial of 0 or 1, and so it's Bernoulli. Likewise, Bernoulli is a special case where you only have 2 categories of the other word that goes with ordinal and nominal. What kind of distribution do they follow? Starts with an M.
Multinomial?
Multinomial, yes indeed. And the term conditional, by the way, means after adjusting for predictors. So the word conditional means leftover. That threw a few folks off. Every single variable that we're going to predict as an outcome has a conditional distribution. If a variable is not being predicted, but it's in the likelihood, then it still has a conditional distribution, but it's the same as the marginal distribution. So that just means, what do residuals look like, essentially? Although residuals is not quite the right word, but you can think of it that way. I think that's a close enough for representation. Leftover, after predictors. After fixed effects, and by the way, after fixed and random effects, if you're in a multi-level model setting where you are predicting a not normal outcome. Okay, questions on that point? So the distinction between ordinal and nominal is not in the distribution. They're both considered categorical outcomes. The distinction comes in the type of link function that you use to predict them. So that's what the other 2 questions were about. So what's the difference between a cumulative Logit Link function and a baseline category or generalized? What do you think? I'm watching the chat window, and I'm listening with my ears. I'm also watching with my eyes if you want to make a gesture somehow. What's the difference between a cumulative and baseline category link function? We got one answer so far. Lumped comparisons versus individual. I like that. Which one is lumped?
Cumulative.
Cumulative. Yeah, so what they have in common is that they both divide up a categorical outcome into a series of binary submodels. That part is the same. And you need C minus 1 submodels for a C category outcome. So if I have 4 possible response categories, then I need 3 binary submodels. The question is, how do I form those submodels? And as Farhan typed, lumping versus individual. Lumping is cumulative. So a cumulative link function divides it up into a series of binary submodels in which each outcome possibility is included in submodel. So if I had outcomes of 1, 2, 3, 4, such as a Likert scale, at this point I'm not even sure which one's correct, and I used to know, it's gone. An ordinal response format, it would be 1 versus 2, 3, 4, 1, 2 versus 3, 4, or 1, 2, 3 versus 4 as the binary submodels. So that only makes sense for outcomes that have a natural order in which lumping something together is a reasonable thing to do. And as a couple of you noted, in that type of cumulative lumped link function, if the model is predicting the lower of the possibilities, then the parameter that goes with that is a threshold. If the model is predicting the upper of the possibilities, then it's an intercept. So if cumulative is lumped, then what is individual? What happens with baseline category / generalized logit? Go for it.
We create submodels based on a category reference, and then we compare the submodels, spec with the baseline. It is like to use a dummy coding variable.
Yes, reference category, exactly. So we have it in the chat window as well as what Vladimir just said, reference category for an outcome. Each submodel then tells you the logit of the other category relative to the reference, given that the answer was one of those two possibilities. So not all answers are in all submodels. They're conditional, they're separated. And a couple of you asked about, well, what about getting the comparisons among the non-reference categories? They're in there. So they're linear combinations of the model parameters. So if I have 0 versus 1 and 0 versus 2, 1 versus 2 is in there as a combination of the two. And that is given to you more directly if you use any of the prediction functions to get the predicted probability of each answer category. So even though the binary submodels don't use all the choices, eventually you can get back whatever you want to know across all of the results, I should say. Okay. Any other questions or comments on number 2?
Yeah, Lisa, I have a question.
Hit me.
So, can you mention again whether these were for nominal or ordinal outcomes, and also what sort of distribution we're looking at? So if it's more than 2 categories, it's multinomial, right?
Yes, if it's more than 2 categories, it's multinomial, and that doesn't care whether it's an ordinal or a nominal outcome, because that distinction has to do with which link function you pick, not which distribution.
And okay, and for the link functions we're using, we're working with the nominal outcomes for these, right?
Well, so here's the
Nominal
thing.
and ordinal, yeah.
Yeah, so that actually segues into question 3. Traditionally speaking, a cumulative link function is for ordinal outcomes in a baseline category or generalized logit where it's like a dummy coding with a reference outcome, that's for nominal. However, you can use a nominal link function with ordinal data. There's nothing wrong with that. So if I have 1, 2, 3, 4, 5 as a Likert scale, I forgot it. I used to know this. Likert versus Likert. Can someone remind me which is correct? Do we care? Likert? Okay. Yeah, I used to know this, and now it's like I've corrected myself so many times I'm not sure which way is right. Likert scale. Okay, we'll go with that. If you really care about each of the answer choices, like you want to know why somebody would pick somewhat agree instead of agree, then you could use a nominal model to answer that question. But if you don't really care about each specific choice and you just want to know what predicts people who say more rather than less as a coarser distinction, then an ordinal model is designed to answer that latter question. So the way to screw this up, let me summarize a different way. What is the one wrong combination that you could do?
I'm thinking adjacent categories with nominal groups.
Depending on how many categories, that may or may not be wrong. Adjacent category is not on the page, by the way, because that's sort of a middle ground between the two. But if you,
Okay.
if you follow that, what could you do that would make zero sense at all? So if you can treat an ordinal outcome using a nominal model, can you take a nominal outcome and fit it with an ordinal model?
No.
No, that's the one thing that would not make sense. Because an ordinal model uses a cumulative link, which lumps together categories above a certain number. But in nominal outcomes, the number that goes with the category is completely arbitrary. So it doesn't make sense to lump together 2 and 3 and 4 in one submodel and then 3 and 4 in another if those aren't quantities that have any kind of direction associated with it. So that's the one thing you can't do, is take a nominal model and fit it with an ordinal, or a nominal outcome and fit it with an ordinal model. So ordinal model means cumulative link function. Nominal model means baseline category link function. And both of them use multinomial as a distribution. And then adjacent category. So this is the one that's missing from here. That is the one where it's a binary submodel, but it's also conditional for only 2 response types in a given model. So it's 1 versus 2, 2 versus 3, 3 versus 4. So given that it was 1 or 2, what's the probability of 2 instead of 1? Given that it was 2 or 3, what's the probability of 3 instead of 2, and so forth. And that one to me makes the most sense. It is hardly ever used. That's the one that corresponds to a partial credit model because there's no assumption of ordering past each individual submodel. Okay, that's the end of the quiz. Any questions on any of that or things you want to go back over?
Yeah, quick question. So in the cumulative model, can we get missing differences by comparing groups like we do for, what do you call it? Generalized outcomes.
Can we treat missing as a category?
No, as in like, you know how cumulative lumps groups together and gives us differences. So can we?
Together? Yes.
So can we like get missing differences like we do for linear model, like missing comparisons? Like for example, it's reference versus B, reference versus C, and then to get B minus C, we subtract them. Yeah.
Yes. Yes, you can. So in ordinal models, it literally happens as a subtraction of one submodel prediction versus another. Let me find, I don't have that slide deck open. It's like you have the probability, say, of a 1 or a 2 in one submodel versus the probability of a 1. You would subtract between the two to figure out what the probability of the 2 is. So yes, even though they're not directly given, you can get the missing comparisons. I understand what you're saying now. The ones that are model implied but not directly given, they are available. Getting that out of software with respect to the predicted logits may be a little bit tricky, but all of the programs will give you the predicted probabilities of each response category, even if it's not given directly by the model and it's still implied by the model.
Okay. It's kind of tricky though because we're dealing with comparisons that are like a 0 or a 1 versus what do you call it? A 0 or a 1 or a 2. Like,
yes, it is very tricky. And this may be a case in which you give up and just run separate models for different things to get the answers directly. I don't see a problem with that in this context. Like, you could run a logistic regression predicting 0 versus 1 and a separate logistic regression predicting 1 versus 2. Dividing up your outcome into literally separate models, not just submodels, but treating it as separate analyses is acceptable. The limitation of doing it that way is that you can't then test differences in slopes across submodels. So you can't say that this predictor is more important in predicting a 2 than it is in predicting a 1. if those slopes aren't in the same analysis. So you lose that type of comparison ability, but if what you really want to know is just different combinations of each treated as the reference in turn, then I don't see a problem with doing that across separate analyses and pooling the results back together again. Where that would break down, though, is clustered or longitudinal data, where you don't want to have to subset parts of the data and estimate random effect parameters using only parts of the data, because then they won't converge onto the same answer again. Interestingly enough, in random effects models that are for ordinal data, the random effects follow the same proportional odds assumption. So there's only one random intercept, even though there's multiple fixed intercepts, and there's only one random slope, even if there's multiple fixed slopes. So having all the data to pool together to estimate that one quantity is important. Okay, thumbs up. Good. Other questions or things you want to go over? Okay, so your next homework is available. It is not due for like 3 weeks because we have spring break and then nothing's due the week after spring break. And so you have plenty of time to work on it. Within Lisa's Centered, this next homework is on the easier side. Now, I wouldn't call it easy, but within Lisa's Centered, it is one of the easier ones I've put together because there's no interaction terms. And there's no estimate statements, I don't think. Everything is just a straight linear model. The question is, what are we predicting now? And there's a few questions in there that are designed to test your interpretation of thresholds versus intercepts. So I asked, for instance, what is the probability for the reference group of a response greater than medium? And then the next question is, what is the probability for the reference group of a response less than medium? So don't think too hard on those questions. Some of them you don't actually have to estimate anything to answer. Because of the properties of logits and probits being symmetric, if I know that the logit of answering a 1, for instance, is a +2, then what's the logit of answering a 0 instead?
The same number, but the negative version?
Same number, but the negative version, exactly. Yep, so if I know that I have a predicted logit of +2 for a probability of a 1, the predicted logit of a probability of a 0 is a -2. In other words, the predicted logit of a 1 is the intercept, the predicted logit of a 0 is the threshold. And they are multiplied by -1 to get back and forth for those. So there's a few questions like that, just designed to reinforce that idea.
Sorry, can you explain that again?
Yep. I will do better than explain it. I have slides on that. Let me open that one. This is lecture 2. I want this slide right here. This is slide 8. Can everybody see that?
Oh, okay, yeah. Now I remember.
Yeah. Remember this part? So if I have a probability of a 1 of 0.99, that corresponds to a logit of 4.6. If I have a probability of 0.01, that corresponds to a logit of -4.6. So they're symmetric about 0, where 0 for a logit corresponds to a probability of 50-50. So if the model tells you what the logit is of the upper category, multiply that logit by -1 to get the answer for the lower category instead. The 0, and I'm doing air quotes, which the YouTubers can't see, the 0 of the submodel, meaning the lower set of possibilities, versus the 1, meaning the upper. Left side, right side. Okay. But we're leaving the land of logits for now, for this week anyway. We'll come back after spring break and revisit them though, because it's too logit to quit. Did anyone check out that video yet? Did you watch it?
Yeah.
What did you think?
It's amazing.
It's
The
amazing.
combination of things, it's incredible, and the rhythm and the lyric is really good. Too logit to quit.
Too logit to quit.
Yeah.
Hey, hey.
Yeah.
Hey,
Yeah, it's
hey.
good.
Yeah, it was like the most expensive video ever made for a long time. Then I think Scream took it over. Janet Jackson and Michael Jackson's video is, I think, most expensive now. Maybe it's been passed, I'm not sure, but Yeah, there was a lot of effort that went into that show. So if you haven't seen it, I recommend it. Like if you're looking for something to watch over spring break on YouTube, right? You can just go down the YouTube rabbit hole of fun videos and things. Anywho, should we put this away? Or any more questions on this? No, we're good? Think we're good? All right. Head back to counts. Why not, right? We're all here. So we were talking about last time where we've been and where we're headed. Everything that we've talked about so far falls under the category of what's known as a discrete outcome. So categorical outcomes, as well as where we're at right now, are counts, which you can only have whole numbers as counts for your data, and so there are certain distributions that only have whole numbers in them that go with this. After spring break, we will get into continuous outcomes that are still not normally distributed, where there's some kind of boundary, for instance, a boundary at 0, and that will rely on our friend Logit with some kind of binomial or beta binomial combination. So these two are coming up after break, and then we're changing gears somewhat to introduce the idea of multivariate models. And multivariate models meaning multiple outcomes predicted simultaneously of all of these different kinds. So counts, the big deal with counts is that this is, let's see here. Yeah, we're on slide 4. Let's start there. The big deal with counts is that they can't go negative. So because of that lower boundary, let me get my mouse on the thing here. There we go. Because of that lower boundary, we need a link function. But we don't need a Logit Link function because Logit Link functions are to create unbounded outcomes for outcomes that have two boundaries, an upper or a lower. This one we only have a lower boundary, and so we can use a log, natural log. So if I put in a predictor, for instance, x, a linear effect of a predictor x in predicting the log is what it would look like in this plot on the left. If I back translate that predicted log count into the original count, the original expected count, it creates a slope that's bendy like this, that has this exponential shape instead. So the inverse link goes from log count back to expected count. The link function goes from count up to log count. So it's the exact same set of principles as Logit's, it's just that it's one level below a Logit because we don't have to take an odds ratio first, or an odds first, not odds ratio. Gotta make sure I say it correct. And as we discussed last time, the expected count can have decimals in it. So there's a lot more possibilities as to what the expected count can be than what the count can be. So for instance, if I have a predicted log count of -1 and I unlog that, exponentiate it, then the predicted count is 0.367. Even though you can't have a count of 0.367, it is predicted as an average. And there was a question, I think Vladimir, you asked about this last week, an offset. An offset, more generally, is any time that you add a predictor to the model but you don't estimate a slope for it. You force it to be a constant that you specify. There was an example in your textbook of doing an offset to test a null hypothesis other than 0. So for instance, if you wanted to test that a slope is 1, and that's your baseline, one way to do that is to put in an offset where you put in the predictor variable, and without doing anything else to it, it's an implicit one that its slope has, and then you can look at a model comparison with that predictor versus letting the predictor have a different slope that's estimated and see if those two are different. If the model log likelihood is higher or the -2 log likelihood is lower with the slope being estimated, then you know that it's different than 1. So an offset, generally speaking, is when you add a predictor to the model but don't estimate a slope for it. What it's used for in this context is to provide a type of denominator, essentially, for the amount of time during which the count was observed. So if you have counts that happen across different time scales for different subjects, then you would want to correct for that difference in time scale via an offset. And so that's an option that's built into all of these different packages that you can add an offset. I don't have that in my example, but there's several in the textbook. And you can do it in any packages, like I said. We're back to odds ratios, except they have a new name. So incident rate ratios is what they are called, but they are just the exponentiation of the slope, same as before. So all of the code that we did before will work for this purpose as well. And the tricky part then, as we talked about, is the conditional distribution. So log link is what we're going with. What it's paired with is going to be the question. Question.
Yeah, in the notation that you have there, when you say that IRR equals 1.25 for x sub I, that x sub I, it is a predictor?
Yes.
But predictors go from 0 to 1?
If
In
it's
this
binary,
context?
sure. X
Okay.
is, in my notation, Y is always an outcome and X is always a predictor.
Mm-hmm.
So this would be
Ah.
like if this was a grouping variable,
Uh-huh.
the presence or absence of something, and if this slope in logs was exponentiated to create this IRR of 1.25.
Okay.
So that's like its odds ratio, but it's not an odds. But it's the
Yeah.
same interpretation. The higher coded group counts that are 25% higher.
Mhm.
And if it were the other way around, then the higher coded group would have counts that are 25% lower. All right, so, sorry, I thought my watch was beeping at me, but apparently I'm just paranoid. Okay, does that make sense?
Yep.
Okay. So the conditional distribution then. I'm hitting the highlights of what could easily be a semester-long course. I'll just put that out there. There's more to it than what we have time to talk about. The one that is the default is rarely going to be sufficient in practice. So Poisson is the standard sort of starting point of what kind of distribution a count variable would follow. The trick about the Poisson is that it is also a one-parameter distribution. So just like Bernoulli has only a mean, but it doesn't have a separate variance for binary data, same story here, where the variance is the mean. They're the same number. It's a one-parameter deal. So on slide 6 here, the yellow line is meant to describe a distribution that has a parameter called lambda, which is the mean and the variance of 1. It would look like this. And do you remember why these are dots here? Why they went to the trouble to draw dots as opposed to smooth lines? Feel free to read from the slide too. This one has an Easter egg.
It's discrete.
Yes, it's discrete. Yeah, so that's just sort of a reminder that it doesn't predict in between values. The original outcome has only integers in it. That means that we can't use a Poisson for things that have non-integer values, like response time or minutes of walking per week, where you can have partial minutes. You can't use this distribution for that type of data. So purple is what it looks like with 4, and then blue is what it looks like with 10. And so after a certain point, the distribution does become symmetric and sort of normal looking. However, this yoking of the mean and the variance to be the same number is the problem. So it's still not normal, because a normal distribution has a separately estimated variance that's supposed to be constant regardless of what the predicted mean is. In the Poisson, the variance is non-constant as a function of the mean itself. So it's not the normal part that's the problem, it's the non-constant versus constant variance part. And practically speaking, if you have a constant variance in a model that should be non-constant, that means that some pockets of the model have less variability and some pockets of the model have more variability than what the single constant number predicts it to be, then your standard errors are going to be too lenient or too conservative in different places as a function of that. And we will see that happen in the example that I have to show you. So this is the starting point. This is rarely sufficient. So there's 3 problems with the use of this distribution, and there are fixes to all of them. Number 1, when the mean is not the variance. So when there's less variance than there's supposed to be according to Poisson, that's known as under-dispersion. I've never seen that happen, although it's theoretically possible. What I've seen happen more often is over-dispersion. And that is a term that is more general than just these models. Over-dispersion as a term means more variance than they're supposed to be. And that will be true of any distribution where the variance is tied to the mean and not separate somehow. So the binomial distribution can have over-dispersion, a Poisson distribution can have over-dispersion as well. So that's the one that we're going to practice with. No zero values is also possible, and then there's too many zero values is also possible. So the first one here, over-dispersion, one way to fix it is to add a parameter to the Poisson that allows the variance to exceed the mean by some function. And this is the one where there's a bunch of different ways to do it. You can have a constant over-dispersion, and that one has been shown not to work very well. So a quadratic over-dispersion is the one that folks have seemingly settled on. And the way to do that is by using a negative binomial conditional distribution instead of Poisson. So in this distribution, the variance starts with whatever the mean is. So just this part right here is Poisson-based. And then it adds this thing that I'm calling K to be consistent with a lot of the literature I've seen. And K is a multiplier of the mean squared. So it allows extra variance as a function of the mean squared. So it's a multiplier that gets estimated. And if K is 0, then the second part drops out, and the first part is just what's given by Poisson. So in this case, we can think of these two as nested models. If you don't need a K, Poisson is sufficient. If you do need a K, then it's like you've taken a Poisson and added one more parameter to it to make it become something else. So we can do a likelihood ratio test to decide amongst these two. And a generalized Poisson is something I've seen mentioned in a couple books. I've never seen it used, but it's out there as well. It's a different way of adding the stretchy factor. And it's better in some sense, but nobody seems to care. So here's what negative binomial looks like. One of the few pictures I made myself as opposed to stealing from Wikipedia. You can think of this as just a stretchy Poisson, because the K dispersion factor adds functionally a positive skew tail to the Poisson that makes it fit count data a lot better. So if you compare the blue line versus the red line, these are both starting out as Poisson distributions with a mean of 5. The difference is that the red line adds a K stretchy factor of 0.25, so it allows the variance to be 11.25 instead, and so it creates that additional skewness. It's even more pronounced if you compare purple versus green. They both have means of 10, but purple has an extra stretchy that stretches out the count to the positive side here. So this is where we do need to use, I think for the first time this semester, a likelihood ratio test. And that is the log likelihood of your model with fewer parameters minus the log likelihood of the model that has more parameters. Then you multiply the result by -2. Or you can take -2 times the log likelihood of the fewer model, subtract -2 times the log likelihood of the more model, and then you come out either way, the same place. And I will show you how to do this in software, by the way. You can also get out Excel and do this, because you can just use the chi-dist function to get a p-value. The reason why we multiply the difference in log likelihoods times -2 is because then that difference is supposed to follow a chi-square distribution. So if I added one parameter, the critical value for a chi-square with degrees of freedom equals 1 for that extra parameter is 3.84. However, this is where statisticians fight about whether or not it should really be 3.84. And some people say, absolutely not, because K is on a boundary where it can't go below 0 and you're testing it against 0, and that's not cool. And so the solution is to use what's known as a mixture chi-square, where it's a mixture of a chi-square of 0, which is not a thing, by the way. You can't have a chi-square with no degrees of freedom, and a 1. So functionally what happens is that you take your p-value and you cut it in half. The use of a mixture chi-square instead of a regular chi-square for this situation in which you're adding one thing and that one thing can't go below 0 means that you can essentially use a one-tailed test. And it's cool. So this is one of the few instances in which one-tailed tests are not voodoo bullshit. They're testing something that can't go the other way. There is only one tail. Fair. You can't have a negative k. So the difference, practically speaking, boils down to the use of a critical value of 3.84 for this test versus 2.71. If you say, screw it, I don't want to learn this and just use 3.84, then you're going to be overly conservative in those borderline cases. I can live with that. So this will show up again in multi-level modeling when we're testing whether or not we need a random component. We're supposed to be using mixture chi-squares for that type of test, and it's a difference like tiny, tiny percent of the time. Yeah. How we doing? So Storchi Poisson. We'll look at that one versus regular Poisson, and then there's a couple more that I want to play with, but I want to explain just one more thing about this comparison, and then we'll look at the example. So clarifying terminology. Do you remember when I told you that if you have categorical outcomes and you pick like a multinomial distribution, you can't be wrong? Like there's only one choice and that's it? That's not true anymore. We can be wrong. Yeah. So when we do something like a likelihood ratio test, this is what's known as a relative fit comparison. Does negative binomial fit better than Poisson? Neither of those tells us if the two models fit at all, right? It could be like negative binomial is less shitty than Poisson, but it's still shitty. We wouldn't know that because these are just 2 points on a continuum. So there's something else that we'll need to pay attention to for any kind of model in which variance is going to be an issue, whether we have enough variance in the model relative to what the data want to have. And that is going to be something called conditional distribution fit. So I want to point out all the different ways in which these two words are used to mean different things. So people talk about sometimes having a nonlinear model. That could mean a model that's not in the linear additive form that we're used to, like slope times variable plus slope times variable. A truly nonlinear model would have like exponents and ratios and stuff in it. A nonlinear model could also be described as a consequence of a slope. So if I put in a quadratic slope to make a bendy line, that could be nonlinear to some people. Or a type of regression. So if you think about the term linear regression, right? Have you heard that term before, like general linear model or linear regression? What some people mean by that is an identity link function. Like it's linear, and it predicts the outcomes, and it stays that way. As opposed to a nonlinear regression, which is what we have, where we're predicting the logit, and that back translates into an S-shaped curve, or predicting the log, and that back translates into an exponential curve. So that word nonlinear means a whole bunch of things, and therefore nothing at all. It's very specific to context. Same is true of the word fit. And I am as guilty as other people at misusing this term, and I'm trying to do better. So sometimes people talk about fit, and what they really mean is effect size. So if I add predictors to a model, and the predictors help the prediction, like they increase the R-square, some people would say that means the model fits better, and I would not. Because fit refers to the adequacy of the distribution that's characterizing the outcome. Effect size is what they're talking about in that case. So Kaylin says, it took me a while to work out what that meant. Linear models versus nonlinear models, presumably. Is that what that comment was geared towards? Fit. Yeah, fit means everything and nothing at all. Like if I had a regular old general linear model, linear regression thing, and I had an R-square of 0.1 and I add predictors and my R-square is 0.3, yay me. Nothing about that tells me, though, whether or not a normal distribution is plausible for its residuals. That has nothing to do with R squared. We sort of assume that that's the case in putting predictors in and talking about how good they work. So you will see in the context of general linear models a whole bunch of examples of use of likelihood ratio tests that have to do with whether or not the model fits better after adding predictors. And I would argue that's not the right term for that idea. You can ask whether the prediction is better, but I don't think it makes sense to say fit. When we get to multivariate models, so this is true in what we think of as either longitudinal data or repeated measures data or clustered data, or anytime you have more than one outcome per sampling unit, then we worry about fit with respect to whether or not the model has adequately captured the variability of each outcome and the covariance across pairs of outcomes. So for those of you who've had structural equation models or who are going to have it this fall, right? Registration opens soon. Come party with me on Zoom or in the room, as it were. In those types of models, we worry about fit all the time. And we will have alphabet soup of fit statistics, different acronyms like RMSEA and SRMR and CFI and NNFI and TLI and all different kinds of letters that all have to do somehow with whether or not the model has adequately captured the covariance across outcomes and the variance of each outcome. And we'll do likelihood ratio tests in that context against a saturated model where everything is perfect to see if our model is close enough to perfect to work for our purposes. But again, none of those have anything to do with whether or not a normal distribution is plausible. All of those tests are assuming it is. So that leads us to what I actually mean, is the fit of the conditional distribution. And how do we know that we actually have something that's plausible, not just better than alternatives, but plausible in and of itself. So this is a new idea that does not show up a lot of the time in what I would call general models with normal residuals. We sort of take for granted that that's good enough. So absolute fit of the conditional distribution is what we're talking about. So in the context of negative binomial versus Poisson, I can do a likelihood ratio test to test whether or not negative binomial stretchy factor helps, but it doesn't tell me whether it's good enough per se. So there is a piece of output that is either going to be given by SAS and stated directly, or I'm going to force it out of R, because of course they don't give it to you directly. But I won, I found it. There's a piece of output that is Pearson chi-square over degrees of freedom. And it is a ratio in which 1 is the goal. Conceptually, what it is the sum over persons of how far off each person is from what the model says they should be, so E basically, divided by what the model says the standard deviation should be at that point. In other words, is the average offness in the data the same amount of offness that the standard deviation in the data of the model tells us it should be? Like, does the data match the model with respect to how much variability is predicted for the residuals? So like in Poisson, if we have a predicted count of 5, the Poisson model says, okay, variance is 5 at that point too. Well, I can actually compute what is the variance at that point and see if it's 5. And if there's more variance than there's supposed to be, then the numerator will be larger than the denominator, and this ratio will be above 1. So we will look at this number as our goal of trying to figure out whether or not any given conditional distribution is good enough, in addition to doing likelihood ratio tests among the alternatives to see which one might be better than another. Okay, how are we doing so far? And then there's one more thing I want to throw in here about negative binomial, and that is you can actually predict the K stretchy factor as a linear model, and I have an example of that because I just thought it was super cool and I wanted to do it. Now here's the thing. Do I have your attention? All of you who are maybe feeling bad about yourselves after midterms or otherwise stressed because you're grad students and you don't know everything yet, guess what? I don't know everything either. And people are paying me to know things and I don't know everything. Do you know how bad that makes me feel every day? Like, I feel stupid every single day, but it's rare that I have proof. Well, today is proof. This is the thing that I screwed up when I taught this course 2 years ago, and I am apologizing to the internet, to all of you, and admitting my mistake, because that's the best you can do, is when you figure out that you've done something wrong, acknowledge it and fix it. So last time I taught this class, when I discovered this Pearson chi-square over degrees of freedom statistic, I was like, oh, cool. Well, that means that I can tell whether normal's good enough, right? How useful is that, right? If it's over 1, then normal's not a good model. Yeah, no. Because in every other distribution for which this statistic is available, there's a denominator. There's a denominator that says what the model thinks the standard deviation should be at that point to judge it against. And look what's not in Gaussian. By the way, what does Gaussian mean?
Normal.
Normal, yeah. If you want to sound fancy, say Gaussian instead of normal. But it doesn't have a denominator. So the Pearson chi-square over degrees of freedom statistic in a normal distribution is just the freaking variance. And I felt really dumb when I figured that out. So no, we can't use this to talk about how adequate the fit of a normal distribution is. It doesn't work that way. And that makes some sort of sense if you think about the idea that each of these others has a variance that is assigned to it as part of the distribution. So Bernoulli, for instance, the variance is the probability of a 1 times the probability of a 0. We haven't got to binomial yet, but it's basically the same thing. For Poisson, Poisson says the mean and the variance are the same, so the denominator is based on the mean. Gamma has a stretchy factor that it's quadratic, but anywho, the rest of these we'll get to. Point being, you can't do this for normal. But there's other things that you can look at to decide whether or not a normal distribution is plausible, but this just doesn't work for that. So otherwise, we will look to see whether this ratio is greater than 1 as evidence that there is more variance in the data than what the model has captured, and that's problematic. There, that's what I wanted to say. Okay, questions before we dive into an example? Okay, if not, this is example 3. We started talking about this last time. The data for this example are not available online because they are real data and they're not mine. So I have full syntax and output for each of the 3 programs, but not the original data. These data were collected by Rosie Maldonado and her lab. David DeLilla was their lab director when she was a student in Nebraska. And I got pulled into this project to help advise on what a good transformation would be to improve normality. I don't think I would have seen this project had there not been very, very close to significant results at stake for someone's master's thesis. But it's a good thing they came and chatted with me because this makes a great example and I was able to fit a better model and get results that are, I think, more believable than what they would be under a normal model. So the paper itself is here. In this example, we're going to look at, I think 6 different models, but starting with normal as a basis for comparison. So the story behind these data, this was meant to be a 2x3 ANOVA. So a 2-way analysis of variance, where these are college students. They were randomly assigned to one of 3 conditions. So in this experiment, they were subject to listen to conversations that were either neutral, were designed to induce jealousy, or designed to induce some other negative emotion. And they were given instructions while listening. And one of them was control, like just listen and do whatever. One of them was cognitive reappraisal, which is like, think about this in a way that's not threatening to you. And any clinical people in the house want to elaborate on cognitive reappraisal? I am a psychologist, but not that kind. So it's like, make it better, sort of. And then suppression, which is just pretend like it doesn't bother you, which we all know how that works, to suppress your feelings. Ill-advised. So those are the three conditions, and then there was a moderator variable as to whether or not each subject had been a perpetrator of interpersonal violence of some kind. And I think their standard was fairly low for violence. Like it could just be, being mean to your partner in terms of not necessarily hitting them, but having emotional issues and stuff like that. So that's my very hand-wavy summary of the study. You can read the original paper here. The data in that paper are slightly different because they had added some covariates to make reviewer 3 happy, and so the sample size is a little different, but the story is basically the same. So let me show you the picture before I go into the coding here. That's the distribution of their outcome for this analysis. It's aggressive verbalizations. Essentially, the number of mean things they said while listening to these scenarios that were designed to piss them off. So somebody came up with 24 mean things to say. Now this is probably an outlier with respect to the distribution, but I'm not going to dump them. Like that happened. Like somebody said 24 mean things. So I don't want to remove subjects for whom I'm still trying to make valid inferences. Most of them, though, said nothing that was mean. So this is an outcome that I would describe as zero inflated upon first glance. That means, wow, I've got a lot of zeros right here, and then some kind of distribution, otherwise that's heavily skewed. So this is very typical for a count outcome. It looks like there's a mixture of people here with respect to, like there's people who just, it didn't flap them, it didn't make them angry, and then there's people that did get angry and they reacted in a way that was codable. So the basis of her question when she came to see me is, what kind of transformation should she do to this outcome to make it more normal? And, well, no. If I took a log transformation of this outcome, that would reel in the tail, so it would be less skewed. But there's nothing that can be done about this giant pile of zeros. There's no transformation on Earth that can take a constant and make it anything but a constant. So my response was, well, let's focus on getting a better model instead of a better transformation, and that's what we did. So these are the residuals per condition. So basically what the residual distribution would look like, it's less zero inflated because some of the presence of zeros was explained by which group they were in, but it still has the same issue of positive skewness in most of the cases. And heterogeneity of variance. So like this condition right here, most of the people were zero, and only a few people were not zero with nothing after it. So this condition has much less variability than any of the others do, for instance. Okay, go back up to the top. So making variables, step 1. So I have ER condition, meaning emotional regulation condition, that I am dummy coding. So I'm treating the neutral or control group as the zero reference group. Then I have cognitive reappraisal, N versus C, and suppression as the S, so none versus suppression. So I'm directly going to get all of my parameters related to the none group, and the none versus cognitive reappraisal, none versus suppression, 2 versus 3 I'm going to have to get as linear combinations. IPV was already coded as 0, 1, so we're going to leave that one alone, and AGGR is our outcome. And in this case, I don't have any covariates, although we could easily add them, but they weren't necessary to make my point. Stata folks, same logic. Start with 2 empty variables, recode them into zeros and ones based on condition 1, 2, or 3. And then the same thing in our start with 2 new variables and recode them into zeros and ones based on condition. So nothing out of the ordinary relative to what we're used to seeing. And I could treat these as a factor variable, but I'm making a decided effort not to. Because how the programs treat factor variables differs across programs too. And I'm trying to streamline all the sources of difference. So we're going to use it just straight up linear coding like normal. Okay. Questions so far? So first thing, descriptives. I looked at the mean for the outcome across the 2 variables that create my 2 by 3 combination. So there's 6 different cells, as they would be called in ANOVA language, 6 different unique combinations of these two, and I made pictures for that, so that's where the histograms came from. I figured out how to do those things in Stata using bisort, so you can get summary output per condition by sticking this in front. And in R, I was able to use the describe by function, but I wasn't able to figure out how to get the same histogram broken down by cells. So if anybody knows how to do that, please send me the code. But here's the summary of the mean across conditions. Now I've highlighted this in yellow because all of the models that we're going to look at are going to predict those cell means exactly right. Why is that? Because the linear predictor is going to have an intercept and 5 slopes in it. So 6 parameters in the linear predictor are going to exactly recreate my 6 cell means perfectly. So all of our models are going to get this part right. This is the expected count per condition of aggressive verbalizations. What the models are going to get wrong, potentially, is this part right here, standard error. The 2 things that go into standard error are the within group variance for that unique combination and the within group sample size. So I've printed those things off to the side here to try and highlight how different these conditions are. First off, there's a whole bunch more people in the no IPV group than in the yes IPV group. So there are more people who have not been mean to their partners, which is a good thing. But that creates an unbalance across cells in the number of people contributing, and thus the precision of the standard errors. The other part is look at the standard deviation within each cell and how different it is. So standard deviation ranges from a high of 5.24, meaning that the average person in this group is off from the mean by 5 on average, versus the average person in this group is off from the mean by 0.3. So this is like the definition of heterogeneity of variance across groups. So a normal distribution, irrespective of the fact that this distribution is zero inflated and hella skewed, a normal distribution is not going to work for this because of this right here. A normal distribution says constant variance. This is not constant. I don't need a significance test to tell me this is not constant. It's just not. So there's 2 ways you could solve the problem. One is to let each cell have a different residual variance. So to actually let it be a heterogeneous variance model. You can do that in all 3 programs. I have that just as a note at the end. I may dig that out later as an example. I haven't decided yet. But the other is to fit a model that allows the variance to change as a function of the mean. And that's kind of what it looks like. The conditions that have the largest mean have the largest standard deviation. And that makes sense for count data because you can only go up, right? There's more variability at the upper end that's possible. You can't go below 0, so the lower end gets truncated. So what we will see is that the standard errors that go with these means vary greatly across models because of the differences in what the standard deviation is presumed to be. And if the standard errors differ across models, so do p-values. Okay, how are we doing so far? So let's see what happened when Rosie fit her ANOVA, because that's all she knew how to do at that point. So it's not her fault, in the same way that it wasn't my fault that I didn't know these models very well back then. So this is my model for everything in this entire handout. It's the same model. Aggressive verbalizations, and I put the hat on it to show that this is the linear predictor part alone, is a function of an intercept plus a simple main effect of IPV, which is going to be, given the interaction terms, this effect for the none group, plus a simple difference of none versus cognitive reappraisal, and given these interaction terms, it's going to be for the no IPV group. Another simple effect of none versus suppression for the no IPV group, and then 2 interaction terms together that characterize the IPV by condition interaction. Whether or not the effective IPV varies across instruction type, or whether the effective instruction type depends on whether you have a history of violence or not. You can think of it either way. In her case, condition was a manipulated thing where she randomly assigned and she gave them different treatments, and so that's the effect she cares about, and she's thinking of IPV as the moderator, because that's a pre-existing difference that they walked into the study with that she measured instead of manipulated. So given this coding scheme and this linear model, they all will tell us who the IPV slope would be for any person. The simple effect of it is the effective IPV by itself, plus any of the terms that have IPV as part of them, factor it out, and then bring down what's left. So just a little bit of review here as how we build simple effects. First off, figure out what you want to know the slope for. Go into the model and find all the terms that have the slope. Bring them down, factor the slope out, and then what's left is what goes into your linear combination to get the slope for each different group. Okay, does that much make sense? Okay, yeah, you've done that, you've done this before. So even though it's a new thing with respect to account distribution, this part's the same. The linear predictor works the same because we're going to predict the log of the count. Likewise, if I want to know about the differences between the instruction conditions, for each one, I go up to the model and find all the terms that have that. So for instance, none versus cognitive appraisal, and it would be beta 2 plus how that effect differs as a function of IPV. So one of my group differences is right here. None versus suppression is right here. And then the one that's not given directly but is still implied by the model would be the effect of suppression minus the effect of cognitive reappraisal. So this is the only one that's not given directly that we have to write out as an estimate statement, but I've written them all out just because it's easier that way. Okay, so in programs then, rather than use a general linear model, I'm trying to keep the results as comparable across these alternatives as possible. So a general linear model is estimated using ordinary least squares, which is the same thing as residual maximum likelihood specifically, whereas all of the generalized linear models do not have a REML, residual maximum likelihood analog, they only have regular flavor ML. So because of that, I'm not using proc-GLM, I'm staying in Glimix, and I'm asking for the model in maximum likelihood. That way, any of the differences that we get are not due to REML versus ML, instead they're due to which type of distribution I'm using. So link equals identity, dist equals normal. What's an identity link? Do you remember again?
It's just itself.
Yeah, itself, times 1. And dist equals normal means normal conditional distribution. So normal shape and one estimated variance that's supposed to be constant, which means standard errors that are supposed to be constant other than differences in sample size. So we have then a contrast here to get my multivariate wald test for the model. So this is like the F test for the model since we're in normal land. And then the 2 degree of freedom test for the interaction. I've got my cell means right here. So these are built using everything in the model, intercept plus each of the simple main effects plus the interaction terms, and setting those to 0 or 1 to go with my coding scheme. Likewise, simple slopes of IPV, and the equations up here is what I'm using to create these. So the effective IPV as a 1 to start with, and then the zeros going with which condition we want the effective IPV in. Likewise, in reverse, we have condition differences as the thing we're trying to estimate, and then for which IPV group we want it. So if we're talking about IPV yes, then the interaction terms turn on. And the tricky ones are right here. So the contrasts that are implied by the model, those are where you do the -1,1 combinations to get cognitive reappraisal versus suppression, given that neither of them is the reference group. And last but not least, simple slopes for interaction contrasts. These two are given by the model. They tell me how the effect of cognitive reappraisal differs by IPV, how the effect of suppression differs by IPV, and then whether those differences are different for cognitive reappraisal versus suppression. Data code looks pretty much the same. Since we're running out of time, I'm going to skip the code and just go to the results, and then we'll pick up the rest of it later. So here's the thing that I said that I screwed up. 11.34 is the residual variance of the model. It has nothing to do with fit. Last time I was all, look at how high that is. It's definitely not normal. No, Lisa, that's not how it works. What I want to draw your attention to is right here. These are my cell means. So these numbers in the first column are the estimated cell means, and they are exactly right. They have to be, because I have a linear predictor with 6 parameters in it, and I've got 6 cell means, and so they're perfectly going to recreate. Now let's scroll across this here, though. I have a note. Proc Lisa says, uh-oh. Why might I have written uh-oh right there? I'm on page 6. What's wrong with this line?
Standard error.
Yeah, what's wrong with the standard error?
It's very high.
It's very high. And what are the consequences of that standard error being high? Oh, we've got the zoomer answer. Yeah, boundary is 0. Here's the confidence interval around that mean. Population mean will be contained in 95% of samples, and it's somewhere between a count of -1.3 and 1.6. Can you have a negative count?
No.
No. So that'd be like -1.3 mean things said. Would they be nice things? Like if you cross 0, do you get nice? Maybe, but that can't happen. So it ends up that I don't even need to have a statistic to tell me whether or not normal is good enough. If I have a confidence interval that can't happen, that can't be good. And the problem is not the mean. The mean describes the data. Only 15% of the people in this condition said anything mean, basically. It was a pile of zeros and a couple of ones. But the standard error for that is based on the idea of constant variance, which we know is not the case for these data and unlikely to be the case for count data. So on the basis of that alone, I would say this is not a good model. And if I can't trust the standard errors that go with each of these means, can I trust the standard errors that go with the mean differences? Probably not. And if I can't trust the standard errors that go with the mean differences, can I trust the p-values that go with the mean differences? Probably not. So a consequence of this model using a normal conditional distribution, in which the normal distribution has one parameter for a constant estimated variance, is that it's going to overshoot some of the standard errors as too high and undershoot others as too low. So that on average it might work, but in the pockets of the model where we actually care about the differences, they're not going to be right. And if these individual standard errors for mean differences aren't right, do you think I can trust these F's and chi-squares for lumping them together? If each individual slope has a standard error that can't be right, do you think it's okay to lump those individual slopes and have it somehow be right? Nope. No. So this was the reason I got involved. I'm quite certain of that. But what we will see is that this number for what the p-value is that corresponds to her interaction, which was the whole goal of the project, was to have an interaction, that's going to change quite a bit as a function of which model we pick, even though the cell means will stay exactly the same. Standard errors come from your variance model, your conditional distribution. Here's a picture that Glimmick spits out about your residuals, and yeah, nothing about this picture is good. There's an overlay of a normal distribution, yeah, that definitely doesn't fit. Here's a scatter plot where the residuals are supposed to have constant variance, and that definitely doesn't fit. The variance definitely increases as you move away from 0. And here's a QQ plot where the points are supposed to be on the line, and yeah, definitely no. So by every eyeball standard plus confidence intervals that go out of bounds, this is not a good choice. So we don't transform the data, we transform the model. But that will have to wait until Thursday. Because it's already 1:43, and time flies when you're talking about log counts. All right, questions before we call it a day? Okay, well, you'll have to live with the cliffhanger. You'll have to wait for Thursday to get the exciting conclusion. I know. Have a good week. Question?
Yeah, I have one. So, in this example, we are looking at the means of the groups because we have variable with categories in the model, but otherwise, if we would be using only numerical explanatory variables, what do we have to do in those cases? Just look at the estimates for each explanatory variable?
Yeah, I think you could ask it to predict the outcome for everyone in the data set and look at the predicted counts and see if any of them go out of bounds.
And in that case, the result would be only one, no?
Well,
based on the different characteristics of the explanatory variables.
Yeah, so there's only 6 types of people in this data set, essentially. So because of the use of categorical predictors and no covariates,
Yep.
these are the 6 possible means this model could create. If I added in quantitative predictors instead or in addition, then yeah, there's more possibilities, and so you would have to do a little more detective work. But still, just asking it to predict the outcome for each case would allow you to see, at least in your data, what happened. That doesn't say that it wouldn't happen in another sample, though.
Okay.
So the same problem, I mean, it may be the case that nothing went negative this time, but the model is still potentially suspect.
Okay. So it is not mandatory to include categorical variables in the linear predictor.
Yes, if you guys gotta go, that's all right. I'm saying goodbye, and I'm answering questions while I wave, so it's okay. Is it mandatory to have to include categorical variables?
Yes.
No. You can do whatever you want. Yep, in the original version of this study, we controlled for their behavior in a neutral condition, and I want to say that reviewer 3 insisted we throw gender in the model and a couple other things they thought should be related to aggressive verbalizations. But yeah, no, it's totally up to you what you put in the model.